So what we're after today is understanding how calorimetry leads us to a state function that we can apply to many, many other systems interchangeably. There's a connection that all thermal released or absorbed energy changes in chemical reactions. It's Hess's law. And that interconnectivity is based upon initially calorimetry. So as I talked about previously, we talked about the idea that constant pressure calorimetry. This is the NASA grade calorimeter. It looked like a styrofoam cup in class, but really it's NASA grade. We don't want people stealing them, okay, and pawning them off for thousands of dollars. That's why they looked so simple. And the idea is, well, they are styrofoam cups because that hole that you thought that was just for the thermometer, okay, actually is a straw. I'm letting you in on the secret. But the point is that we can use these nested styrofoam cups and get very good data, very accurate data. Certainly there's going to be limitation, and I want to make sure that even though we don't have a more advanced type of bomb calorimeter, we actually prefer to use this nested constant pressure calorimetry. It's constant pressure because the openings allow air pressure to go in and out, so the pressure inside and outside, okay, is not closed. There's interchangeable and in equilibrium. So the pressure in this container is the same as the pressure. It's not a sealed container like below here. So this is actually advantageous because many reactions work under constant pressure. Many biological and chemical reactions are in constant pressure calorimetry. And more importantly, constant pressure, as I'm going to show you, leads us to a state function we can get directly from the thermal heat that we measure in calorimetry. So as simple as these are, okay, these are very important types of calorimeters. But before we go on, let's remember that calorimetry is a study of the internal system. If we have a chemical that's going to react, we say that the Q of the system stays constant. Energy released, okay, Q negative, equals energy Q positive absorbed. So we would say Q of the chemical equals Q of the negative Q of the what? Water. All right? The problem is we're assuming that this is an isolated system and that no heat is being exchanged with the environment. Well, that's not so true. Okay, no matter how expensive we use, how expensive calorimeters can become, there's going to always be some leakage of heat outward, and that's a product of the second law in thermodynamics, where concentrated energy wants to diffuse outward. So we're going to lose some heat, and so all of our errors, however minimal, there's going to be a loss of heat. So therefore, a system will lose something, and our values that we measure are usually going to be underrepresentative of what they actually are because of the heat loss outward. Now the bomb calorimeter, more expensive, it approximates a more isolated system than this does, but okay, it's constant volume calorimetry and the values we get from it aren't nearly as helpful as the ones in constant pressure. And let's continue. Okay, so if we look at delta E, the first law of thermodynamics states that the heat of the system plus the work of the system equals the internal energy. And we know that at constant volume, it will change, and we'll put these little subscripts of volume here. What does that mean? So the change of the energy overall is state function. The internal energy is equal to the thermal heat, okay, at constant volume, just like the work at constant volume. All right, and if we did constant pressure, we would change these subscripts. We're doing so to tell the people who are using these values what kind of conditions are we at. Now, interesting enough, and maybe not, we know that the work of the system, as we said before, is equal to negative of the external pressure times the change in volume. This gives us joules, pressure times the change in volume. All right, now, more importantly, all right, at constant volume, calorimetry, there's no expansion of work. Okay, that's important. Constant volume is what's going to happen in a bomb calorimeter. That's the more expensive Grotsky grade calorimeter. Okay, there's going to be no change in the volume or because we're in a closed system. The pressure is going to increase, and that's why it's not constant pressure. So the work done on the system, or the work that the system does on the environment, will be zero because it's what? Closed off from the environment, whereas the constant pressure is not. There is some openings. So this change in volume is zero. And so therefore, right down here, party people, what we get in constant volume calorimetry, the Garotsky grade, the Bob calorimeter, the more expensive one, is that the change of E equals the thermal energy. That's still good. It's nice to have a state function, okay? And that's a good thing, but not one that we use often enough because, again, most of the energy changes occur at constant pressure. So this is where enthalpy comes in. So we look at enthalpy as delta H, and we've used this. If you had another course, it popped up in many places. And so where does it come from? Well, it comes from the idea, here we go, First Law of Thermodynamics. What do we know? We know that the thermal heat plus the work of the system under constant pressure. So what do we know? When we rearrange and solve for the thermal energy, we get change of E is minus the work at constant pressure. What do we know over work at constant? Negative P, change of V. So we're going to plug this in right there, and what we get is something called Q of P. We're just rearranging, remember we just rearranged this, Q of P. We're going to put in the work equivalent here, right there, and that's what I get down there. So what we get, party people, once that dissipates, at the bottom left you see H, which is enthalpy, equals the energy plus the PV. So what we have is we've basically made ourselves a new state equivalent or state function that we call H, enthalpy, and it's equal to the energy plus the pressure volume. So what's interesting is that we were able to take a path function, Q of P, and we're able to make it into a state function. And you say, well, why do we care so much about enthalpy? Because most reactions occur under what? Constant pressure. So we have to consider the work that's being done. And why is there work being done? Because the volume is expanding by either pressure changes or temperature changes. So very important. So interesting enough, we call it enthalpy. Unlike Q, it's a state function composed entirely of state functions. And now this is what we can use. We can use this delta H, enthalpy, which is a change in overall energy, as we're going to show you in a second where we get this from. But it helps us able to interconnect all other enthalpies. Because of the state function, I don't care about the pathway, I care about the stopping and starting, and that's going to help us with something called Hess's Law. But in any case, let's look at this. So we're left off with this, and then if we do some changes of H equals a change and do our math, we wound up getting this value. So delta H equals a change of E plus the pressure times the volume at constant pressure. And that's what enthalpy is. We're never going to actually use this part, but I want you to understand that enthalpy had its roots where? Had its roots from the Q that we measure from calorimetry. Right, party people? Let's go back. I know, why go back? But the Q that we get of P that we just got in our labs, hey, that is equal to enthalpy. The problem is enthalpy is often measured in energy per amount, per mole of something, and that's why we divide it by moles. We never just talk about that. But now we have a value of basically enthalpy, or a state function that's equivalent to a path function. So this path function in calorimetry opens the door for the possibility of interconnectivity with other reactions. And what do I mean? Well, let's talk about that. And what is this interconnectivity? Well, here we go. All right, so let's talk about Hess's Law, which is the connectivity of enthalpies. Once we have this state function, which again we get from the constant pressure calorimetry, we can use these values for any kind of reactions to answer questions using the interconnectivity of delta H's. Let's just get into it so we understand what we're talking about. So let's talk about this for a second. I'm going to talk about some reactants. I have nitrogen and 2 oxygen gas molecules. When they react, we're trying to make 2NO2, but there's 2 steps to the reaction. All right, first I make O2 and 2NO. So N2 reacts with 2 oxygens. Now the delta H here, if you can see it, is positive 180. Okay, that means it, generally speaking, it needs energy, or overall energy is absorbed in this spontaneous reaction. So the delta H is positive, it's endothermic. Now, so these reactants become these products in this reaction. So the overall energy change was basically consuming 180 kilojoules. All right, now this chemical, which is the same thing as here, reacts to make two NO2s. And the energy is released to negative 12. And again, because I'm using enthalpy as a state function, I don't care about the pathway. So think about it. I went from here to here. That was positive 180. I'm going from here to here, negative 112. Well, what's the difference? 68, which means if I want to make N2, N oxygen, to make 2 NO2, the overall energy change is 68. You may say, well, big deal. Well, it is a big deal because I don't have to do the reaction. If I have calorimetry data that gives me this reaction going to this reaction, and I have calorimetry data that gives me this reaction to this reaction, I can clearly solve the enthalpy of this becoming that using this interconnectivity. Okay, I'm going to write this out again, and I'll say it one more time. I know the energy change from this reactant to these products. You can measure that in calorimetry, constant volume. I get my enthalpy in kilojoules per mole. And then I take this reaction to this, then I know the difference between these two without doing the reaction. Yes, I can know my delta H's without doing the reactions. What if the reactions I want to perform are expensive? I have to do them in large quantities. I don't have the materials. I don't have the equipment. Reactions sometimes are not as simple as one step. They require unique conditions, and I can't do that. I can get the energy change and figure out the energy change of a reaction that I did not do using energy changes of other reactions that are related to it. That's the power of Hess's law. And I want to show you that. So hold on, let's go on to my worksheet here. All right, so let's look at this another way. So I've got these two-step reactions. So we're starting with N2 and 2O2, and it took 180 kilojoules of heat to make the O2. So this is step 1. Okay, and then O2 and 2NO2 reacted to make 2NO2, and this is step 2. We already know the energy to go from here to here and here to here by someone previously doing some calorimetry work. Okay, what's really cool is I can find this delta H here without doing the work. And here's how you would do it. Okay, if these reactions can be manipulated in a way, okay, to give us the overall reaction, then we can manipulate the delta H's to get the overall delta H. Now in this case, very simplistic case, I can see very clearly that when I look at the first step and the second step, okay, that there is 1O2 on this side, 1O2 on this side, 2 NOs and 2 NOs. And the overall reaction is N2 plus 2O2 gives me 2NO2. So in this case, when I put them together, I get the overall. Well, whatever I do to the reactions, I do to the delta H's. Why? Because they're state functions. I don't care about what pathway I took. Whether I go 1 and 2 to get this product. Remember, we're trying to make what? We're trying to make this reactant becomes this product. Now, if I chose this pathway, 1 and 2, what I'm doing essentially is I'm going to add both these up. And when I do that, delta H, okay, is equal to 68 by adding them. Essentially, by putting these together and letting them cancel, they're adding. And I get the kilojoules per mole, which means this value from here to here is 68. Now, we didn't do it directly. I took different pathways, and it doesn't matter because I'm using state functions. So part of Hess's law is understanding that if I have energies of related reactions that connect to another reaction, I can manipulate these steps as long as they cancel out to the overall step to get this value. So no, I did not do N2 plus 2O2 to get here. I used entirely different set of reactions that overall does what? Cancels out to the one-step process that I didn't do. And using the energy, now of course this would be Q at constant pressure, I was able to get these values, or I get them out of a manual or some book. And as long as the reactions cancel to the overall, and sometimes I may have to times by 2, divide by 2, do something, whatever I do to the reaction, I do to the delta H, again because they're state functions, add them together and I will get the overall. So clearly I was after N2 plus 2O2 to make 2NO2. And it is 68 kilojoules, and I got this value not by doing any calorimetry, but by using values already established by other reactions that are connected to this one, using a totally different pathway. All right, and that's what's really cool about Hess's law, is that every single delta H is interconnected, okay, to other delta H's somewhere down the line. In this case, very simplistic case, these two steps canceled out to give us the overall, and therefore the delta H's added together, just like these reactions canceled together, really being added together, gave us the overall. All right, and that's one form of Hess's law. So let's go to our worksheet tonight. All right, so I've got two reactions here, carbon graphite going to CO2 and carbon diamond going to CO2. You can see they're kind of related, because if I wanted to measure the energy of graphite going to diamond, maybe I can't do that. Maybe I don't have the facility or the equipment to create the pressure and temperature to take carbon, okay, and make it into diamond, which we can do industrially now. But if I know reactions, if they're interrelated and I have their enthalpies, state functions, I can get the overall. So here's how we do that, okay, very simply. So here's what I'm going to do here. Take these delta H's, and I'm going to basically try to manipulate these set of reactions to the overall. All right, now I see carbon graphite's a reactant, and this one's a reactant. Okay, so that's my first step. So I know I'm going to rewrite this one this way. And you may say, why am I going to rewrite them? It's really helpful to do that when they get a little more advanced. But you see this carbon diamond? This one belongs on the product side. So I'm going to swing them around. And again, I get these reactions and their delta H's from known values through a manual. Remember that big book I have in class that I raise over my head? Okay, those are different types of manuals that have all different types of reactions. Fun to go through on a Saturday evening. But well, I'm going to do a little bit live for you. So in any case, I'm going to take this graphite and rewrite it. C graphite, I'm just going to put for graphite, plus O2 gives us CO2. And I'm just going to keep this value, just kind of square it off. And then I'm going to flip this one around. And the reason I'm flipping this around, because this is a product. So this is going to become CO2 plus carbon diamond, little d here. And this is going to make, I'm sorry, I know I messed up there. Okay, so yeah, flipping around sometimes I can't flip around too well. So CO2, right, I can get this, equals C diamond for the D and the O2. Okay, now this one's spun around, and understand this. If something is exothermic, giving off energy in the forward, if I'm going to spin around, remember, negative signs are directions. So if the reaction's going to go in the reverse, what can you expect the sign to be? That's right, this goes positive. All right, so this becomes a positive now. And of course, if we check it out, when we add these or put them together, now everything cancels except for C graphite goes to C diamond, is what we wanted. So I just manipulated these interrelated reactions that are in a manual, or I picked the ones that I wanted for that purpose, okay, and now I'm going to add these together. Now because I flipped this one around, I flipped this sign, add them together, and what I get is a 1.9 kilojoules. Now I'm putting kilojoules, it's probably per mole. Always energy per mole with delta H's. Okay, so I'm able to actually gather this information without doing the reaction in calorimetry. Okay, I'm circumventing that. Let's move on to number 2. All right, Same idea. I want to know the energy of this reaction, but I can't do it, can't afford it, don't have the system, don't have the lab. But what if I have reactions that I know that will cancel out to the overall? Because delta H's are interconnected, I can do it. So P4O6 is a reactant. I don't see any reactants here except here. So I'm going to flip this one around. So I rewrite it. So I go, maybe this time I can do it right, P4O6. Okay, big arrow, P4 plus 3O2. Now I'm flipping it around, so I'm going to make note that I'm changing this sign. Okay, now I have P4, okay, on this side. I'm not changing this one because the P410 is a product, so I don't want to change that one, so I'm just going to rewrite it this way. So P4 plus 5 O2s, big arrow, gives me the P4O10. I didn't change this at all. The direction stays the same, so the sign. Now, what am I trying to do? Well, I'm trying to write this overreaction. P4O6 plus 2 oxygens gives me P4, that's a 4O10. All right, well, I know that my P4 cancels, and I have 5 oxygens and 3 oxygens. Well, there's a net what? Well, I'm losing 3, I'm starting with 5, so there's a net gain of 2, right? That's why the 2 is here, so I did this correct. And all I'm going to do now, this cancels, which is basically adding, all right, these two reactions. I add these delta H's together like I've done, and I get approximately, when I round off, about negative 1,300 kilojoules. Okay, so that's how I did that. Now, that's not always that easy. Fact number 3, going to get a little tricky. Let's try number 3. All right, so same idea. We're trying to use a set of reactions that if we manipulate them, we can get the overall reaction. Delta H's are state functions. So let's get to it. I need C2H4 as a reactant. Ooh, this is a product, so it's the only place where it is, so I'm going to flip this one. So I just kind of make a mental note, and I make this negative to remind myself, and now I'm going to write C2H4, as we say in my town, and then we go to 2C plus 2H2. All right. Now I need some F2s, and all my F2s are here. Okay, we can do this. And 2 CF4s. Okay, so basically I'm going to write that. Now, write it out. So I got my H2 plus my F2 gets me my 2HF. Then I got my C plus my 2F2, and that gives me my CF4. Okay, so what are we trying to do? We're trying to get this reaction at the end. So I have C2H4, I'm good. I need 6 F2s. Whoa, we only have 2, 3. There's a 1 in front, right? Nothing in front is 1. So not good. So let's continue. Let's see here. I need 2 CF4s. The only place where I have CF4 is here. And I need 2 of them. So what we do is, to get 2 of them, we have to times everything by 2. And using the distributive property, this gives me 2 C's. This becomes a 4. That's getting closer. And this becomes a 2. So I distributed the 2. And I did that because I needed 2 CO2s. If I multiply, remember this is an equation, right? So if I multiply both sides by 2, everything's the same still. That's all I did. And that's a good stuff. Now, I need 6 F2s. I only have 5, so I need a 2 here. Notice I need 4 HFs. I only have 2, so clearly I'm going to do the same thing. I'm going to times this by 2 and distribute the 2 all the way through. 2 times 2 is 4. And then we're going to see what we have here. We have 4 plus 2, that gives me my 6 F2s. 2 CF4s we have for my products. We have 4 HFs, and everything else better cancel, okay? And lo and behold, two H2s, two H2s, two C's, two C's. So how do we deal with this? Whatever we did with these reactions to manipulate to get this reaction because of the interconnectivities of the enthalpies, we do here. So we do 2 times negative 537 plus, remember, canceling out, we're adding together, 2 times negative 680 plus negative 52.3. Put that in your handy dandy calculator, and what you get is negative 2486.3 kilojoules, which got around to at least 3 sig figs. So I go negative, and I'll clean this up, 0.49 times 10 to the 3, and that's kilojoules. They don't say mole, but we can assume mole, okay? So if you didn't want to use scientific notation, it's negative 2490 kilojoules per mole, okay? So in that case, I had to do that. So 1, 2, and 3 are pretty straightforward. Try your hand at number 4, okay, and leave that alone. So try number 4 on your own, and look for the key. Now, after you do that, okay, I would like you to take out your lab and look at the first 2 reactions that you did and see if you can manipulate them with their corresponding delta H's, okay, to give you the third reaction. Do the first 2 reactions. Can you manipulate them like we just talked about them using the delta H's we got from calorimetry? Can you predict what the delta H should be from using Hess's law? Okay, I'll say that again. I want you to take the first 2 reactions in your lab. We should have written them out already. And I want you to do this type of manipulation, and I want you to cancel them out to get the overall. This is reaction 1, reaction 2, and reaction 3. So the first 2 reactions should be canceled out some way to get the overall third reaction. And I want you to compare the value you get by adding these 2 together, if you manipulate them correctly to get the third. Does that approximate, okay, the value you get from the delta H directly by calorimetry? Now that completes the lab. Try that. Okay, so finish number 4, go back to your lab data and do that. Yes, we're done.